And recording is on. Yeah, so welcome to Monday, another week. You guys having a good Monday so far? Had a good weekend? All right, so I'm sure. Yeah, we're gonna go with we're gonna turn things around, make things good. Hey, I've got at least this good news for you. This upcoming weekend is 1.5 times long. So yeah. So if you're coming from the bad weekend, well, I guess you get 1.5 times that. Oh wait, okay. I'm trying to frame things positively. So I got this starter question for you guys that maybe some of you guys have solved already. We'll do an activity with the ruler. We'll do a few problems from the textbook, and then tomorrow I'll do as many from the book as I can. I'm going to start projectile motion with you guys in a couple of days. In fact, if you want a head start on it, there are a couple of papers clipped to your desk. There's one on the right side of your desk. Right? So if you want it early, you can grab it already if you want. We'll get to it for a couple of days though. And then there's another page on the front of your desk. That's just for you guys because you guys are AP. So again, just recap. The one on the right side of your desk is some good like starter warm-up problems to get the foundation for projectile motion. And the one on the front of your desk are the college physics textbooks problems that we're eventually going to get to. It's going to take us some time. Okay? All right. This question. Take a ball, throw it upward at 50 meters per second, which, by the way, I checked. That's about 112 miles an hour. So let's say that you could absolutely Nolan Ryan this thing straight up. How far up does that thing go? If you throw it up at 50 meters per second. Okay. Who figured this out? Who knows how high that ball's going? Who figured it out? Yeah, Xander. About 125 meters. Wait, that's the answer.
Wait, that is?
How'd you know that?
College.
Of course, college. But, well, I'll walk you guys through it from a couple of different perspectives. And you guys can get what Xander got, right? So I'll start with a very roundabout way. Guys, a very roundabout way. These are all good tools to have, like good mental tools, because sometimes you want to have different approaches. Or a lot of times, AP will ask you a question in a very abstract way, so you need like different ways to approach things. Right? Because if you throw something straight up at 50 meters per second, then how fast is it going after 1 second? 40. Maybe it's like here at 40 meters per second. And after another second, 30. Okay, so we're 2 seconds up, it's 30 meters per second. Then another, now it's 20, then 10, then 0. Because it'd be losing 10 meters per second, wouldn't it? It's going up, gravity's pulling down. Doesn't that take you 5 seconds to get up there? 5 seconds? Okay. And look at the symmetry of this problem. If it's 5 seconds up, you think it's 5 seconds down? And how far does anything fall in 5 seconds? It's about 125 meters. Good college problem. And isn't that just this here? Doesn't this top equation relate time to distance, like distance and time? See, the other two don't. Like the second one doesn't say how far. The third one doesn't say how much time. But the first one, right? And then now that's if you drop something from rest, which effectively isn't that like half this problem? Like if you start from the top and just drop it and it falls for 5 seconds. Okay? So dropping from rest, what I'm trying to get at is what happens to this term? Just goes to 0, right? Your initial velocity 0. So it just boils down to x is half at squared, right? If you plug in stuff, 5 seconds falling, 5 5 is 25. Half of a, that'd be also 5 meters per second squared, half of 10. Right? It's about 125 meters, right? Now, that's, like I said, that's the sort of roundabout way to do it. I wonder if there's maybe a more direct way. Right? Oh, speaking of time, before I go on to that, can anybody tell me what's the total hang time of this ball? The total hang time? 10 seconds, right? 5 up, 5 down. Okay. All right. And I want to point that out too, because when I say maximum height is a really classic fundamental physics question. What's the maximum height something goes? And somebody pointed out last week that I know for sure Xander caught and a bunch of guys did too, is what's the speed at the very top? 0. Right? So that starts, now you can start to check off boxes of what variables do I have. So these motion questions, you're always going from some point A to point B, initial to final, start to finish. So we've located the 2 places, here and here. Okay. Right. Maybe you use the TAX-VB checklist framework. Okay. Here's the 5 variables that we're juggling around. Okay. Okay, well, I did explicitly give you one of the speeds, right? Now, if you want to do them throwing up, or throwing the ball upwards, what a pleasant Monday, then you could do that perspective. Or alternatively, you could do this. You could say, well, based on symmetry, maybe your brain prefers to do this. I'm just going to cut this problem in half and do the falling half. Maybe it falls and lands at 50 meters per second, right? You go either way. So let's say 50 meters per second. Right? What else do you guys know? Acceleration. So I'm just going to use 10. Is that okay? 10 meters per second squared. Right? If you want 9.8, that's fine. AP will take either. So just pick your favorite for the AP exam. That's two things. You got to know the third thing. What's the third thing you know?
Final velocity.
Final velocity is 0 meters per second. Right? Now, if you said time, that was the first way we did, like a roundabout way. And we figured that out. We reasoned through it by stepping through the problem. But we knew to stop time. We knew to stop counting out 5 seconds because the velocity at the top was 0. So that was the more immediate thing that we would know, right? Okay. Right, so that's it, right? Hang on. Something very wrong here. If this guy throws the ball upwards, which way is gravity pulling? Down. Uh-oh. Do we have a mismatch in signs? The way gravity's pulling and the way that the guy's throwing, shouldn't those be opposite directions? Yeah, somebody's got to be negative, right? Because if they're both positive, it's not like the ball's like rocking me up, like flying into space. Right? That's what would be going on. Right? Somebody's got to be negative. What do you guys feel like today? Is up positive or is down positive? Down. Okay, that's what we did all last week. So let's stick with that convention. So we'll call this positive and this negative. Okay. Right. Okay. So that's our checklist framework. Now, again, the roundabout way that we already solved it is that we did basically the second formula first and got time 5 seconds. And we took that time and plugged it into the first one and got 125 meters. But do you guys see the equation that will let you solve this directly in one shot? It's going to be which one? The third one. Right? Anytime you have this mix of variables and you want to know how far, right? How far? Yeah, third one will get for you. Notice that the third one doesn't mention how much time has passed, so you can just bypass that step. Remember, this actually is the solution to the system of equations of the first two. Anyway, let's do that. Let's go. Final velocity squared equals initial velocity squared plus 2ax. Right?
Mr. Griffin.
Yeah, go.
Doesn't matter which way you say it's going to be positive or negative. Like you say up is positive instead of.
Great question. We've been calling down positive for pretty much all my examples, haven't we? Right? If you wanted to reverse the definitions, if you wanted to say up is positive and down is negative and swap these signs, would you still get the exact same answer? Huh. Right. Tell you what, do you want me to spoil it or do you want to find out your own by yourself?
Spoil it.
Spoil it? Okay, yeah. All right, so spoiler. You will get the exact same thing. It doesn't matter which way you call positive or negative, as long as you stick to the convention throughout the problem, right? In fact, you know what I want to do with you guys? Since you guys are AP, let's solve this in terms of variables. See, my honors classes, I went ahead and plugged in the numbers. So let's call this number -50, call this number 10, and then after that, do the algebra. But with you guys, have the skill that we're about to do. Can you solve in terms of variables? And then plug in the numbers after the fact. I bet you guys can do that. See if you can stay a step ahead of me. We're going to do a bunch of steps, and at the end get x equals and something in terms of all these characters. Okay? All right. I hope you guys got a head start, because I'm going. See if you guys can beat me to the end. It's a physics race. So subtract v naught squared over, divide both sides by 2a.
So is this just algebra?
Yeah, just algebra, but in terms of variables, right? Okay. Oh, that's it. X equals b squared minus b naught squared, all divided by 2a. Right. Now, that's the general solution. Right? So, now you see what you can do with this is that you can plug in like any numbers you want. Like you could have different throwing speeds, like lots of different people throwing. You could even change planets if you wanted to. You could take this guy to Mars and say, like, I want to change out the acceleration and make it like 3.7 meters per second squared for Mars or 1.6 meters per second squared for the moon. And you could get different heights, couldn't you? You guys see the weaker the gravity, if A gets smaller and smaller and smaller, X is going to blow up bigger, bigger, bigger. Ooh, interesting. The bigger the gravity, the higher you can throw. Okay. Let's plug in some numbers though. Okay. So how far? Now final velocity was 0 in the context that we set up, being squared, minus initial velocity was negative 50 meters per second, and that term is also being squared, divided by 2, 10 meters per second squared, like that. Okay. Is that okay so far? Okay. Let's run the numbers and see what happens. So negative 50 squared is positive 50. I've got, oh, whoops. What did I do? No, yeah, we're good. Okay. So that square is 2,500 divided by 20. Okay. I'm getting a negative number. I'm getting negative 125 meters. Is that right for that number to be negative?
Yeah.
Hold on. Which way was the positive direction? Down? We defined it that way, right?
Yeah.
Just coin flip? Right. So by throwing it negative, that means it went which way? Up. Hey, this is up. This is up 125 meters, isn't it? Yeah. Now, what if you did this? What if you swapped the negative signs, like you called this positive and this negative? Right? Would that change the sign?
Yes.
Okay, in this case it does, right? And that actually brings up another point that I want to mention about this. So this particular equation, every once in a while it'll run you into trouble, and so you have to do a mental check and make sure that all the numbers are okay, because you could possibly lose the negative information by squaring the terms, right? When you square the terms, you lose that negative information, right? So yeah, just keep that in mind too, right? Okay. Every once in a while that gets you off track. All right. Any questions about that? Yeah. All right. So you guys can solve a maximum height problem. I want to ask a question. How could you guys test your reaction time? Would you guys believe that there is a delay between what's happening in the outside world and your brain making sense of it? Right? It's a good fraction of a second too. Now, that's something that sort of by definition is imperceivable, right? Like me speaking and you hearing it, besides the time for sound to travel. That aside, once the sound hits your ears, right, there is a fraction of a second delay for your brain to process that. Right? Maybe most notably, you would notice that if something was happening quickly, like either you're driving a car and you know something in the road and you go to slam on the brake, I think there's a tiny delay to hit the brake. And maybe in retrospect, you sort of notice it, like, right? Or something like flying right at you, like this flying right at your face, like, oh, I gotta catch this. Right? There's like a tiny delay. How could you measure that delay? Now, time, you normally use what instrument? Like a stopwatch. But the problem with using a stopwatch to measure time delay is, I mean, we're trying to measure the very error of starting and stopping is sort of what we're trying to get at, right? Can you guys think of something, maybe an instrument that's on your desk you could use to, Xander's holding up a ruler, right? How could you use this to measure your, yep, take a look at Xander, see what he's doing. Boom, exactly. Right, you guys see that? So, here's our setup. About to get you guys in pairs in a moment. Okay. So, say that one person is holding a ruler. And another person is ready to catch that ruler. They got like this crab-looking hand right here. Now, notice where I drew him ready to catch this thing. It's like right at the 0 centimeter mark. And you guys are using centimeters, right? Centimeters, not inches, right? Right. So then this guy on the left drops the ruler, and this person on the right catches it as fast as they can. And then when it makes sense that the distance that it fell has something to do with time delay, let me get a table going. Do a 3-part table here. Okay. Let's go trial. Let's do 3 trials, maybe like 3. Right. How far did it fall in centimeters? I'm gonna give you guys that much. Right. Now, before you guys get going, just want to point out something. Just make sure everybody's on board. Well, you guys are AP, so I'm sure you wouldn't miss this. But what if you start off with your fingers like right at the 15 centimeter mark, and then they drop it and you catch it at the 20. Does that mean it took 20 centimeters for you to catch it?
No.
No, probably more like 5, right? Right. Or what about this? What if you hold your fingers like this and then you catch it like, man, I'm catching it at the 1 centimeter mark. Are you that fast? Probably not that fast either. So that's why you want to start at the 0, because however far it falls, you can just read that number, and that represents how far it fell, right? Let's get this as a measuring tool for how far, right? All right, so go ahead and get in teams of 2 or 3. Two or three is fine. Go ahead, take a couple of minutes and try this out. Everybody get some react. Find some long distances. We'll put it together.
Why do you have fast reactions? You're not holding no, what? You didn't bring your body. Oh, no, he's not with the speaking. He's not.
All right, get your last measurements. Last measurements.
I just want to see it. I got a 9 for that.
All right. You guys ready to go? So everybody's got a few at least. All right. So this is not anything I'm picking up. It's just for your own knowledge. Now you can know what the time delay is between reality and your brain. So let's say I'm just gonna make up some numbers that are maybe somewhat representative of an average person. An average person might catch this at, let's say like 22 centimeters, and then like the 27, and then like 23. I'm just making up some stuff. Hey, now, based on falling distance, how many guys went all the way and figured out what your reaction time was in seconds? Anybody go that far? Okay, well, let's figure it out. Which one of these three amigos is going to be most helpful? First, second, or third? The third, which has nothing to do with time. So that is quite futile. How about the first? Hey! Doesn't the first one represent the relationship between distance and time? It's the only one. The second one doesn't say how far the roller fell, or doesn't address it. And the third one will never give you reaction time. It may give you the speed of the ruler, but this one here, yeah, distance time. In fact, guys, if you drop the ruler from rest, I hope you guys weren't throwing the ruler down, being mean to each other. Like, oh, you're so slow. You guys drop it from rest. What's this term equal to? 0. So doesn't it just boil down to how far the ruler fell is 1/2 gt squared? Right. Well, I'm saying g because it's free fall gravity type of acceleration, right? And we really want to know, what is this time? Okay. Can you guys solve this in terms of variables before I do?
So should we average our times together?
Yeah.
One for all?
That's a question too. It's like, hang on. Should you average the distances and then take the time, or should you figure out each individual time and then take the average? Right? You actually will get slightly different numbers. I would say take each one of these individually first and then average the times. Yeah, Eddie?
Are we allowed to, for the 1/2 AT equation for the speed of gravity, just put 5t squared?
Yeah, basically, yeah. You can do that. Call it 5 meters per second squared collectively. Yeah, half a g, right? Let's see. By the g down, 2x on g is t squared. Here we go. Did you guys get this? The reaction time is 2 times the falling distance divided by Earth gravity. Is that what you guys got? You guys got that, right? Okay. Now, this is the general formula. Right? Again, general because you can plug in lots of different falling distances. You might have a few, right? Like my example does. Right? Hey, you could also change planets if you wanted to. You could go up to the moon and just drop some rollers. That was some good use of government funding for the space program. Okay. Let's see. How far would this be? Let's see. I should probably do. Let's set up one of these examples. Got square root of. Try my first one. 2. The falling distance was 22 centimeters. Gravity. You guys want to use 9.8 or 10 for this? 10. Okay, let's use 10. Extra round number.
Which would make my reaction time?
Let's see what I get out of this. What is the square root of 2 by 22 on 10? That's, and then this column would be time and seconds. I'm getting, hey, 2.1 seconds. 2.1, guys, were you sitting there for 2.1 seconds waiting for the roller to fall? No? That would be something wrong. There's something wrong about what I did. Yeah, Olivia?
You need to convert meters per second or centimeters per second.
Boom! Guys, this number 22 that I plug in, that's centimeters. Yeah. How can you convert that to meters? Divide by 100, right? So this is actually how many meters? 0.22. See, guys, see, if I said 22, it's not like 22 of these guys fall into your hands. You're like, whoa. For like over 2 seconds. Right? That's not what happened. Right. Well, what about this? What if you caught it at the 8 centimeter mark? 8 centimeters. What number would go here? 0.08. Yeah. It's always 2 decimal places, right? And so I'm gonna pop in a decimal right here and get, that looks a lot better. 0.21 seconds. We try 27 centimeters, getting 0.23. And what about 23? 0.21 again. Okay, well, there's more digits, but we take the average of those. There's 21, 3. About 0.22 seconds, like that. Okay. Yeah, that right there is pretty representative of the average person. The average person. Right. Show of hands. How many of you guys got a reaction time that's faster than that? Faster than that?
Well,
Hey,
that's-
guys see that's about half of the room? Yeah, that's how averages work. About half you guys a little faster, half you guys a little slower. That average?
What's the fastest one that you've gotten so far?
I don't remember. Yeah, sometimes people catch these in like the single digit. But I don't know. That's kind of maybe luck, luck too. You just do few. Have you guys ever heard the challenge where you hold a dollar bill? You basically do this with a dollar bill. Supposedly, it's like nearly impossible to catch the length of the dollar bill. So I don't know.
No, if you have them hold it up the middle, it's impossible.
Oh, if you hold it in the middle.
Yeah.
Okay, yeah, I'm sure that would be important. Yeah, because that's only a few centimeters at that point. Okay, yeah, so if you hold it at the middle. All right, you guys want to try some textbook problems? Yeah, I can't wait to do some. Okay, so I'm going to be referring to this page. What I'm going to do is pull some problems that look very similar to some of these, and then you guys can follow along and make sense of those, right? Let's start off with I'm going to do one that's kind of similar to number 6. Let's say number 6 very similar too. Okay. Yeah, and number 6 has a position versus time graph going on. Okay. You know what? If there's a position versus time, maybe I should set this up like I'm going to ask my own questions too. So set up a couple here. A couple of axes.
So, Mr. Griffin,
Yeah.
did you say all these papers you gave us were just like practice things?
Oh,
Or these homework?
okay. So got a question about what's going on with the homework. All right. So here's the deal with this. You guys remember this court page from a while back? All right. So upcoming this Friday, you guys have a page that looks like this. Then I'm about to do some. They're basically off the page. Right. And the page looks like this. You guys remember we solved like 3 of these scenarios last week? Right.
Yeah.
Right. Now, between these two, pick at least 8 and write those out and turn those in. Now, guys, when I assign homework, I usually assign something that's like very minimal, and there's some reasons for that. One reason is that, like psychologically, like if you have a goal to like at least do some minimum, then you can more easily get momentum. And then once you're working at it, you're like, oh hey, these are actually pretty fun. Maybe I want to like go extra, do some extra stuff. It works that way. Yeah. And different reasons too. Like if you do, if you pick 8 that look really challenging and you get those like, piece of cake, then hey, you're good to go. On the other hand, if you just pick out some and you realize you're struggling a lot, then you know that you personally need to probably pick some more problems and try some more. Also, you guys know that all the solutions to these are on Google Classroom, right? And the 2 pages that are clipped to your desk right now, there's one on the front, one on the side. Those are referring to these 2, which are due next Friday, not a few days, but next week. Right? And then you guys know AP Classroom, I want you guys to have turned in by the end of this Labor Day weekend so I can go over this next week. Yeah, Marisa?
So, is it like 8 for each?
It could be like 4 and 4, 3 and 5. Again, that's like the minimum that you want to do, but that's what I give full credit for. Yeah, sure.
When we turn in the homework on Friday, do you want us to have it, like, all the work written out?
Yeah, just like everything written out, your answers boxed at the end. Yeah, just so I can see like, okay, yeah, put in the effort that, get there. Oh, Jacob.
Wait, so you do want us to turn in our work?
Yeah. Well,
I did some of the work like in my notes.
oh, okay. Tell you what, if you got your notes and you need it there, just for the one with the boxes on it, then I'll be right. I know what's going on. Yeah, let me get this. Oh. Okay. All right. Who else had it? Oh, yeah. This one.
If we do any alternate assignments, it's just one assignment for the whole homework grade. If you're gonna have to do it for like 2 separate pages.
Yeah, it's all just one thing. Yeah, so if you like pick 4 off one and 4 off the other, just put it all together. Yeah, that's right. Okay, so some stuff's coming up. Yeah, I guess I should say if if you're solving these out of the book, then definitely write out your work, then I can see it and follow your steps and know what you did there. Okay. All right, so I'm going to make up my own problem that looks similar to number 6. Now, number 6, they give you a position versus time graph. All right. 2, 4, 6, 8, 10. So 1, 3, 5, 7, 9. Okay. So that. Oh. Now I'm going to make up my own graph that doesn't look exactly like the book one. Maybe I'll do something like this. Like that, and there, 10. All right, and then let's call, I need to give you some position values. Let's call this negative 10 meters and like 10 meters. Okay, just make up some values. And then just be the 0 meter mark. All right, you guys good? All right, so first let's see if we can figure out a story for what's going on. What's going on with the, right? Maybe somebody starts at the 0 meter mark, right? And then just starts walking. No, this could be just like forwards and backwards, right? This is just linear motion, right? Okay. So it's like this person's walking forwards for a while for the first couple seconds. What's this person doing for seconds 2 to 4? Yeah, stand still, right? And then, thanks. Right. And then looks like this person's walking which way? Backwards. And then at the 5-second mark, they're at the exact same place they started, right? And they just keep on walking backwards and then forwards, and then at the 10-second mark, now they're back where they started again. Right? So this is the actual motion of the person. Let's say like forwards, backwards, right? So they went forwards, they stopped for a while, they came back, then immediately turned and went back where they started. Okay. Right. Can you guys draw a velocity versus time curve for that? Velocity meters per second versus time in seconds. See if you can beat me to the answer. All right, you guys got a velocity versus time that you think looks pretty good? I would walk around the room, check, but save a minute here on that. All right, so guys, this guy starts walking at exactly what speed?
5 meters.
Yeah, 10 meters divided by 2 seconds, isn't that like 5 meters per second? That's the slope of that line. Okay. So, oh, whoops, I forgot to put my times on here. 2, 4, 6, 8, 10, thereabouts. Seconds. Okay. So during the first 2 seconds, this guy was walking forwards at 5 meters per second. Right? 10 divided by 2. Okay. Okay. Then what happened? Stop. Was that basically at rest for 2 to 4 seconds? Or something like that? Right? Notice on the x versus t, remember how a lot of our x versus t graphs were like parabolic? Okay. That's definitely not true here. There's no like curvy lines, so I'll just a bunch of, I used my ruler. Okay. So notice the velocity versus time is just like constant values. No, it jumps around a bit. But, okay. How about between 4 and 6 seconds? What's this guy doing? Yeah, it'd be negative 10 meters per second, wouldn't it? Because isn't this change 20? Like negative 20, I should say. Because what's negative 10 minus 10? Negative 20. And it took 2 seconds to happen, right? So that'd be negative 10 meters per second. So it's like this segment down here, right? Takes us up to the 6-second mark. Okay. And what about these last 4 seconds? What's this guy doing?
2.5 meters per second.
You're right, 2.5 meters per second. So the 2.5, I guess these are okay numbers. And he's up from scratch, but worked out pretty good. Nothing crazy. All right. There you go. That's velocity versus time, right? Okay. Oh, how about this? Oh, take a look at that velocity versus time curve that we just made. Okay. What property of this graph tells you how far this guy went? Now, how about this? What's the unit for distance? Meters. What property of this graph tells you some number of meters? Area, right? Like you guys see some rectangles? Looks like look like buildings up here. Maybe we got like the Bat Cave down here. You guys see some buildings? Okay. They have a height in meters per second and a base in seconds. Isn't this some area in meters? Okay. Hey, between the beginning and the end, what is this guy's displacement? 0. He ended up exactly where he started. Do you think that this positive rectangle plus this positive plus this negative rectangle exactly zeroes out? Let's see if it does. It better. Let's see. What's 2 seconds by 5 meters per second? Isn't that 10 meters? So you did 10 meters. Oh, hey, that lines up with that, doesn't it? 10 meters. Okay. How about this is 2 seconds wide by negative 10 meters per second. Isn't that negative 20 meters? Right? Ooh, that's going from here to here. Went backwards 20. And then 2.5 times 4 is 10 meters. Right? What's 10 minus 20 plus 10?
0.
0. Ends up right there, right? Okay. How about this? If you are asked displacement, the answer is 0. If you're specifically asked the word distance as a scalar value, like your car odometer is just adding up all the distance you go, what's the total distance that this guy walked? Yeah, 40, right? Because you just take the absolute values, now all those together. Okay. How about this? What is the average velocity? Go back to, look at this first graph we can get, right? V bar is called average velocity. If you see a bar over a variable, just a plain bar, not an arrow, just a bar. Okay, an arrow per second vector. Okay. Between, let's say 0 to 4 seconds. 0 to 4 seconds. Okay, so during first 4 seconds. Okay. What was the average velocity?
2.5 meters a second.
It is 2.5. Because you guys know you would just do, you'd be looking at this line here, total distance over total time, or I should say total displacement over total time. You guys see, between first 4 seconds went a total of 10 meters in those 4 seconds. So the 10 meters in 4 seconds is 2.5 meters per second. Okay. So if you're ever asked average velocity, you look at total displacement over total time. Okay, you guys good? All right, how about, right, let's go on a road trip. You guys want to go on a road trip?
Yes.
Woo.
Absolutely.
Okay, so let's say we got, you're driving. Okay. The driving time, hold on a minute, how do I want to phrase this? Okay, never mind. Let me go back. Okay. Driving speed, that's what I meant. Let's say your driving speed is equal to 70 miles per hour, which we won't use those units very much in this class, but just for this one. Okay. Right. And let's say that you took a break, say a break time of 15 minutes. Right? So that by the time you arrive at your destination, your average speed, average velocity, came out to be only 60 miles per hour. Scratch this. Okay, so these are your given values. Right? So when you're out on the interstate, you're going pretty much constantly 70 miles per hour. You just do that right? Until you pull over for gas and then like go grab a sandwich and then get back on the road. And that whole break only lasted 15 minutes. You're just like in and out. Right? Question I want to know is, I want to know two things. Right? What was the total driving distance? And what was the total trip time? Can you figure those things out? Right. I'm going to give you guys a head start. Give you guys a minute to think about that. Sure, it's all a minute. All right, so there's different setups you can do. There's different approaches. I'm going to just pick one approach and get to the end. If you want a totally different approach, then that's right too. All right, so, okay. Let's see, what's one way I could do this? I could solve this in terms of total distance, right? Total driving distance, right? So total driving distance. What is this all equal to? Right. Well, it could be. A minute, did I?
I don't know how you're supposed to find.
3 times 3.
I don't know how to figure how long and how far at the same time. What we have.
Yeah, sorry, man. This would be like a system equation thing. I'm looking at my. I do. Okay. Gotta ignore that. Sorry, guys. I'm gonna have to start this from scratch. Okay. Right. Well, let's see. Total driving distance. You could do driving speed times driving time. Can you do that? Okay. So you could do the speed that you were driving times the time that you were actually on the road. Right. And you could also do the average speed times the total trip time. Okay. Now, those are all different things, aren't they? Right. Which numbers do we actually know? You know your driving speed was 70 miles per hour, but you don't know the actual time that you were driving, so that's unknown till you drive. Okay. You could do, hey, you know your average speed came out to 60 miles per hour, okay? But you don't know the total trip time. Okay? That looks like two equations with two unknown, or sorry, basically they're both equal to total distance, but we have two unknowns in here. Right? They're all equal to each other, so it's like one equation, two unknowns. Okay? There's one more relationship where you can make a system of equations. Do you guys know the relationship between these two times, the driving time and the trip time? They're different by how much?
15 minutes.
15 minutes, right? So could I say this? Could I say the time for the trip is equal to the drive plus 15 minutes? Is that too good enough? Is that? All right. Hey, you know what I could do then is I could take this expression, I could substitute it right up into here. Replace that, right? And then since this is equal to this, then I would just have one unknown, and that one unknown would be the driving time. Okay? Okay. Now, like I said, there's different ways to set this up. If you look at the solutions that I gave you guys, I actually set it up a slightly different way. Okay. There's one more idea that we have to reconcile, which is the time units. We got hours versus minutes going on. Right? But let me make the setup, just get started. Right? So I know that 70 miles per hour multiplied by the driving time, that's this right here. Okay. That would be the total distance, right? Which is also equal to 60 miles per hour multiplied by the driving time plus 15 minutes. Right. But guys, if I want to reconcile all these units, maybe I could just take care of that right now. It's 15 minutes. How many hours is that if I want everything in hours?
A quarter.
A quarter of an hour, right? So wouldn't it be 15 over 60 hours? Yeah, that would be a quarter of an hour, wouldn't it? Okay, guys see that? Hey, maybe take this 60 miles per hour and distribute it. Is that okay? Okay. So then I'll have 70 miles per hour times the time to drive is equal to 60 miles per hour times the time to drive, plus, looks like, okay, the 60s cancel, the hours cancel, I get 15 miles. Right? Like I said. Right. Hey, miles per hour times the driving time. If I'm solving for driving time, that's like solving for x. Okay, just subtract that over. Get 10 miles per hour times t drive. That's 70 minus 60. That's where I got that. Is 15 miles. That's true. Divide both sides by 10 miles per hour. Okay. Now the number, okay, 15 divided by 10. The number is 1.5. What's the unit? It's 1.5 what? Hours. Yeah. Right. So that's 90 minutes. Okay. Now that's just the time on the road. Okay. Actually, I don't think I even asked that time or that question. I did not. I asked two questions. Actually, neither of them were exactly that. Asked the total trip time. Actually, we can knock that out right now, guys. If that's for driving time, what's your total time? Oh yeah. What's that, Ryan?
How were you able to subtract the 60 if you were multiplying it in beforehand?
Yeah, I got 70 times x. I got 60 times
But
x.
I mean, it was part of a multiplication thing. You just
Yeah.
subtracted it instead of dividing.
Exactly, because I'm adding over the 15, right? So it's kind of like this. It's kind of like saying, here, I'll rewrite that. 70t equals 60t plus 15. Right, see, I could just subtract the 60t over. 10t equals 15
But the way you originally wrote it at the very top, you were,
up here.
shouldn't you? Oh, wait, okay. never
Yeah.
mind, I see.
Okay, yeah, so you're good. Yeah, so did some little bit of distribution there. Right. So you guys right there. Right. But where we are here is we're going to say if you add the 0.25 hours of the break time, right? That gives you 1.75 hours for a total time. D total. Right? All right, now that's the total trip time, right? So answer that question. But I still need the total driving distance. How many miles did I just tack onto my odometer, right? Okay. Now there's actually two ways to solve that. You could figure out your average driving time times the average driving speed. No, sorry, driving speed times driving time, or you could do average speed times the total time. You can do either one. They should give you the exact same answer, right? So let's try that from both points of view. I could do x equals the driving speed times the driving time. Or I could do the average speed times the total time. Okay? And, well, I'm gonna leave it up to you to apply your mental creativity and figure out why those two have to be the same thing, right? This is the sort of thing that, like, as an AP student, you gotta be able to figure out yourself that you could do them all. But I'm gonna show that they are the same thing. So my driving time, just numbers I made up, was 70 miles per hour, right? And I was really only driving on the road for, what's our number, 1.5 hours, right, 1.5? So 1.5 hours. Okay. Versus the other setup, it was averaging 60 miles per hour if, when you include the break, right? But including the break also means that you have to tag on those extra 15 minutes, which is a total of 1.75 hours, right? So either perspective, I should get the same number, right? Let's see if this is true. Moment of truth. What is 70 times 1.5? That's 105 miles because the hours cancel. Okay. So that was the distance that I drove. Was that also the distance of the trip? Well, it's got to be. Let's see. What's 60 times 1.75? This is all being recorded, so please don't kill my recording. Oh, it's 105 miles. Look at that. A couple of ways to approach that. Okay. Guys get there? So basically, can you set up a system of equations, solve it that way? Okay. One more thing before you guys take off. There is problem number 20 that looks very similar to what I'm about to draw. It gives you an acceleration versus time graph. Let me do it this way. Let's do acceleration versus time. Then I want to make a velocity versus time from this. Okay? So put time on this axis, put acceleration here, put velocity here. Okay? I'm just going to do this as general shapes, just to. I would throw some numbers on here, but when you get to for the bell. Okay. So let's say that you've been accelerating at this value for a while, okay, and then suddenly you immediately accelerate, let's say a huge negative value, something like that. Let's have an acceleration versus time curve that looks like that. Right? Questions? Can you craft a velocity versus time based on that? And I will give you one value. Let's say it starts from rest. Doesn't have to, but usually does. So let's do it. Start from rest. Guys, can you draw a velocity versus time? Looks like during the first, maybe it's like a 3-second interval, something like that. Okay. During the first couple of seconds, you're just kind of moseying on up. Hey, guys, what property of A versus T tells you acquired velocity? The area under the curve. Remember, this is meters per second squared. This is seconds. So this area represents some number of meters per second because it's meters per second squared times seconds. Right? That gives you acquired velocity. That brings you up to like here. Right? Then, oh boy, this is a huge negative rectangle, which is also represents some number of meters per second, doesn't it? Except it's negative. Right? Those two rectangles look, I don't know, maybe pretty similar size. Let's say the same size. Let's say it's like 20 meters per second and negative 20 meters per second. Right? Right. When does this graph finish off? Looking something like, go like that. If the rectangles cancel out. Okay, so here's what you'd be given in the textbook, something very similar to this. You can craft velocity versus time. Hey, could you take this and turn this into a position versus time? I think this would look like a, well, let's guys think about that. Right. What does position versus time look like? You figure out what that would look like. Maybe some parabolas, right? Right? Maybe some parabolas. See something speeding up, then I see maybe like a car braking to a stop. Can you put 2 and 2 together? Figure that out? All right, guys have a good Monday.